We present Stochastic MPC with multi-modal predictions for traffic intersections. This is joint work between UC Berkeley and Ford. According to a NHTSA report, 36% of all crashes on the road occur at intersections. The leading causes are mostly due to human error and misjudgment. Autonomous vehicles are being deployed in real traffic scenarios to improve safety and efficiency and face these same challenges. In this work, we look at how to address partial observability of the state of other drivers. Now we get into a problem formulation. The eco-vehicle must plan its controls over an n-step horizon to track a predetermined route while avoiding the other agents, which we call target vehicles. We are given multimodal predictions for the target vehicle, which operate within a finite set of behavior modes. For example, in the figure, the TV can stop, turn left, or head straight, as indicated by the colored ellipses. Given TV multimodal predictions, can we find an EV control policy that maintains safety while tracking the route? The key insight is that because TV positions can be observed, we can incorporate the ability to make future observations into our planning framework. This provides flexibility to react to future TV realizations. Using a chess analogy, a conservative approach would be to find a single sequence of moves that is robust to all possible combinations of the opponent's next n moves. Instead, we find a strategy for each combination of both players' next n moves. We apply this idea in our stochastic MPC formulation by optimizing over a sequence of feedback policies. In our approach, we look for a sequence of controls to minimize the EV's route deviation, subject to collision avoidance and state and input constraints. The controls are given as feedback policies that are a function of the EV and TV realizations. This allows for different TV responses to each TV realization. Here, if the TV yields, the EV responds by turning. If the TV turns, the EV yields. And if the TV heads straight, the EV turns and follows. In contrast, prior approaches to this problem find a single sequence of inputs to satisfy all the constraints. Here, the EV has to plan a single response for all likely realizations of the TV under all modes. As a result, the EV chooses to yield. In general, these fixed input approaches are conservative and less likely to find a feasible solution. We evaluate our approach on the right in Carla and compare it to a SMPC baseline on the left that doesn't optimize our feedback policies. Here, the EV turns left and the oncoming TV drives straight. We see that the baseline becomes infeasible and deviates more from the left turn route. In the second scenario, the EV turns right and the oncoming TV turns left into the same road segment. We see that the SMPC baseline becomes infeasible again due to large prediction uncertainty. Our SMPC, on the other hand, is able to find a feasible solution and reach the goal faster. Here, both vehicles turn left. We see that the baseline turns to avoid the TV and ends up becoming infeasible, deviating significantly. In contrast, our approach slows down and turns minimal deviation, remaining feasible throughout.